please print off this handout if you haven't done that already. Here we're talking about empirical formula. So this is a formula that shows the lowest whole number ratio of the elements in the compound. And this is derived from experiment, and that's actually where the word empirical comes from. It's a Greek word, empirikos, which means by experiment. So this empirical formula is the formula that's derived by experiment. And I'm going to show you how we develop that today. And this is different than the molecular formula, which I will go through in the next lesson. So for example, let's look at two different compounds. Here we have benzene and here we have acetylene. Now I'm showing you their molecular formulas so you can see that they are different compounds. I've also given you some properties. So benzene is a toxic liquid, acetylene is a flammable gas. So they have different properties as well. However, in both of them, if you look at the ratio of carbon to hydrogen, it's the same. It's a 1-to-1 ratio in both. So both of these compounds have the same empirical formula, 1 carbon for every 1 hydrogen. So the empirical formula is a good start to finding out what a compound is, if you're not sure what it is, but it's not the final step. That's what we're going to look at in the next lesson, but for today, we're just going to figure out the empirical formula. So I would like to show you a couple examples here of how to find an empirical formula. So in this example, we're analyzing a sample of iron oxide, and we want to know what is its formula. So in our lab, we're going to analyze the substance, and we find that there are 132 grams of iron and 56.8 grams of oxygen. So what we're going to do is we're going to set up a table like this. Now I've already set it up for you. I find it helpful to set up my table like this. It just helps me stay organized. But the basic idea is we're going to find the number of moles of each element present, and then we're going to find the ratio between the different elements using those mole values. So we have iron and oxygen. Those are the only elements in my sample. And in the question, I'm told there are 132 grams of iron and 56.8 grams of oxygen. In order to calculate number of moles, first I need to know what the molar mass is. So these I just looked up on my periodic table. Molar mass of iron is 55.85 grams per mole. Oxygen is 16 grams per mole. And just recall, to calculate number of moles, it's mass divided by molar mass. So I'm going to do that calculation here. I have mass, I'll divide it by molar mass, and I'll end up with the number of moles. So in this sample of iron oxide, I have 2.36 moles of iron and 3.55 moles of oxygen. Now the next thing I'm going to do is find the ratio of iron to oxygen. In order to do that, I'm going to find the lowest molar amount. So in my list of molar amounts, this is the smallest one, 2.36. So I'm going to divide each molar amount by 2.36. So of course 2.36 divided by 2.36 is 1. And 3.55 divided by 2.36 is 1.5. So we can see here that for every 1 iron atom, there's 1.5 oxygen atoms. But that doesn't really make sense because you can't have half of an atom of oxygen. So what we need to do now is change this ratio, 1 to 1.5, into a whole number ratio. So if you are comfortable with arithmetic, you can just easily notice, well, if I multiply both of these by 2, I'll get a whole number. So 1 times 2 is 2, 1.5 times 2 is 3. So my ratio of iron to oxygen is 2 to 3. you need 2 atoms of iron for every 3 atoms of oxygen. So now I can figure out that my empirical formula is Fe2O3. I'm just using my ratio of iron to oxygen, 2 to 3, and that becomes my subscripts. So that is finding an empirical formula based on mass information. My next example is pretty much doing the same thing, except we don't have mass information. Now we have a percent composition. But the process is pretty much the same. I'm going to start with listing all my elements in the sample. I have sodium, chlorine, and oxygen because that's what I'm told in the question. Sodium, chlorine, and oxygen. Now, the next section in my table was mass because I need mass divided by molar mass to find the number of moles. But I'm not given any information about mass. All I have is percent composition. So for this, let's just pretend that we have a 100-gram sample. If my sample is 100 grams, how many grams of sodium would there be? Well, it's 21.6% sodium. So that means in a 100-gram sample, we would have 21.6 grams of sodium. So I can just fill in my chart like that. I can just change my percent composition values into a mass value. So I can just say in my 100-gram sample, there's 21.6 grams of sodium, 33.3 grams of chlorine, and 45.1 grams of oxygen. Now the process is exactly the same as I did before. I need to find my molar masses using my periodic table. Sodium is 22.99 grams per mole, chlorine is 35.45 grams per mole, and oxygen is 16 grams per mole. Now I can calculate the number of moles. Mass divided by molar mass, and I'll do that for each one. So now I have the number of moles of each element in my sample. I'm going to do the same thing before to find the ratio. So I'll find the smallest value, which is this one, 0.939, and I'll take each molar value and divide by the 0.939. So for this calculation, the numbers end up being a lot nicer. I already have 1, 1, and 3. So I don't have to do any extra math to find my whole number ratio. So this means that for every 1 sodium atom, there is 1 chlorine atom and 3 oxygen atoms. So my substance is NaClO3, 1 sodium, 1 chlorine, 3 oxygens. It ends up my sample was sodium chlorate. So that's how you can use mass or percent composition to figure out an empirical formula of a compound.